Hey, Denellen High School, this is Mr. Ayton, and this is the AP Chemistry Review. Right here in this podcast, we're going to be taking a look at shapes. We're going to be taking a look at bonding. We're going to be taking a look at trends. So let's start that review. Let's start off with shapes. Here we have three different shapes. We have CH4, we have NH3, and we have H2S, which would be very much like H2O. And when we take a look at the shapes of these guys, of course, the first one's going to be tetrahedral. Then we have trigonal pyramidal. And then we have a bench shape, and you can see the difference is the unshared pairs of electrons, the number of unshared pairs of electrons. All of the hybridizations of each of these guys are all the same because they all have 4 bonding sites, so it's sp3. Remember, 4 bonding sites is going to be sp3. What about their intermolecular forces? Their intermolecular forces are, of course, the tetrahedral would be London dispersion forces. The NH3 would be hydrogen bonding, and the H2S would be dipole to dipole. Hydrogen bonding, remember, is when an N, O, or F is shared or has an attraction to an H. And last but not least, let's take a look at our bond angles. Our bond angles are 109.5, 107, and 105. And why does that continue to decrease? Because the number of unshared pairs repel more, and they're going to increase. Let's take a look at some other types of shapes. We have SF4, we have CLF3, we have BRF5, and we have XEF4. Take a look at where this is on your periodic chart, and let's take a look at our shapes. Of course, the first one is seesaw. The second one is T-shaped. The third one is square pyramidal, and the last one is square planar. Okay. And if you saw an XEF2, that would be a linear shape, and it would still be, that would be an sp3d. And so, of course, five bonding sites is going to be sp3d. 6 bonding sites, like an octahedral type shape, is going to be sp3d squared. Let's take a look at how to draw Lewis dot structures. Lewis dot structures, remember, count up your total number of electrons, put the lone atom in the center, fill the outside with single bonds with octets. Add any leftover electrons to the central atom. If there's less than an octet on the center, move to make double or triple bonds. If it has equal or more than an octet, you are done. Let's take a look at our bonds. What we know about bonds: stronger bonds are going to be triple bonds, but longer bonds are going to be single bonds. Single bonds are going to be 1 sigma, a bond order 1. Double bonds are going to be a sigma and a pi, a bond order of 2. Triple bond is going to be a sigma and 2 pi, a pi sandwich there, and that's going to be a bond order of 3. Here are some common and resonance structures that you have to know. Really take a look at these. Make sure you know these and can draw these, because these show up all the time. We have NO2 with that 1 lone electron. We call that a free radical, which means it can dimerize. When does it dimerize? It dimerizes when it's in solution. When is it NO2? When it is in a gaseous form. Okay? And so that goes from NO2 to N2O4. We have SO2, sulfur dioxide, which is kind of a bent or angular type shape, and those guys have bond orders of 1.5 because it's an average. And both bond lengths are exactly the same, and they're between a single and a double bond. And of course, ozone down at the bottom right there. Okay? Those are three different resonance structures that you got to know and show up all the time. Let's take a look at some bonding here, and you can almost answer these questions yourself. What's the difference between H2S and CO2? H2S is going to have a greater melting point and boiling point because it's polar as opposed to nonpolar. Remember, polar things are asymmetric. They have polar bonds and they have an asymmetry. Nonpolar things like CO2 might have polar bonds, but it has a net dipole moment of 0. What's the difference between H2O and H2S? Well, H2O is hydrogen bonding, H2S is dipole to dipole. Hydrogen bonding would be greater intermolecular attraction. Both I2 and F2, they're both London dispersion forces, but what separates London dispersion forces is a greater number of electrons gives it more of a chance of an instantaneous dipole, or more polarizability. Okay. We have NaCl is a solid, H2O is a liquid. NaCl is actually a crystalline solid because it is ionic, where H2O is just hydrogen bonding, purely covalent there. Let's take a look at some more. LIF has a higher melting point than CSBR. Look at where they are on the chart. LIF is much, much, much smaller ions. Li plus and F minus are very small, which means a greater attraction in them, a greater lattice energy. It takes more energy to split them apart and melt it. MgO and NaF. MgO has a +2 and a -2 in the ions, which means greater charges, greater attraction, greater amount of lattice energy in order to split and melt that intermolecular attractions. SiO2 is a solid, CO2 is a gas. SiO2 is, of course, covalent network, where carbon dioxide is just covalent there. And then NH3 is soluble in water. Remember, like dissolves like. And hydrogen bonding things attract to other hydrogen bonding things because there's high intermolecular attractions there. And so the O of the H2O would attract the H on the NH3, and the H on the H2O would attract the N on the NH3, but not something nonpolar like C6H6, benzene. Okay? Let's take a look at, when we take a look at our trends, we can always explain every single one of our trends with a couple different things. Number one, look at the number of protons. If there's a greater number of protons, and this is going to be when we take a look at horizontally on the chart, okay? You take a look at a greater number of protons, that those protons exhibit an effective nuclear charge. It exhibits attraction to the electrons because they're different charges. So that's effective nuclear charge. Do that number one. If that is not different, go to shielding. Shielding is what we're going to take a look at with our vertical trends. Vertical trends. Okay? If there's less completed shells or less shielding, of course, the outside electrons are closer to that nucleus, which means there's a greater effective nuclear charge. And number three, if the protons are the same and the shielding is exactly the same, go to your number of electrons. And we know electrons repel electrons, and so that will make it larger, okay, on that electron-electron repulsion. So let's take a look at some things and see if we can explain them. Li is smaller than CS. This is a vertical trend, and so we're going to go with less shells, less completed shells. There's greater effective nuclear charge, which makes lithium smaller. Let's take a look at O is smaller than lithium. This is a horizontal trend, and so O has a greater number of protons, which makes a greater effective nuclear charge, and therefore it's smaller. We have S negative 2 and Cl negative. These are both called isoelectronic. They're both like argon electronically. Their electron configurations would be exactly the same as argon. And so the answer to that is that the less number of protons, we go to protons, the less number of protons for sulfur makes less effective nuclear charge, which makes it larger. And then we have, last but not least, we have O minus 2, which is like neon, is larger than O. And the reason for that is they have the exact same number of protons, but they have a different number of electrons. Greater electrons give greater electron-to-electron repulsion. Let's take a look at some more trends. Here we have K is smaller than has a smaller first ionization energy than Br. This is a horizontal trend, so where are we going to go? We're going to go to less number of protons, less effective nuclear charge, which means less energy to remove an electron. That's ionization energy, energy to remove an electron. Then we have CS is smaller first ionization energy than Li. This is a vertical trend, and so we want to take a look at radius. Larger the radius means smaller effective nuclear charge, which means, of course, less energy to remove an electron. And then something we should know is that the second ionization energy is always greater than the first ionization energy. And the reason for that is once an atom loses an electron, its effective nuclear charge increases, and therefore the energy to remove an electron increases. That happens for absolutely every single element. We have the equation or the reaction for ionization energy. Remember, ionization energy is the energy to remove an electron. So this would be like, and it takes energy. So sodium plus energy, it's endothermic, equals Na plus an electron that he lost. And then electron affinity is the energy released when we gain an electron. An F plus an electron, it's gaining an electron, it releases energy. It's exothermic. Now guys, on electron affinity, some of these reactions might need energy to gain an electron. Something like a noble gas would need energy, so that would be a reactant. Keep in mind things like when we have first ionization energy, second ionization, third ionization energy, we're looking for the jump, and the jump, of course, is from 2 to 3, so we're only going to lose 2, which would be an alkaline earth metal. And then something like boron has a lower first ionization energy than beryllium. Boron only has one valence electron in its p orbital, which means that energy to remove that electron is a lot less than the full s orbital. Okay. Remember that all atoms, especially the transition metals, they're going to lose from the s orbital before the p. And that is all my shapes, my bonding, and my trends. Good luck. Hope this vodcast went well, and good luck on that AP exam.